The exponential decay function is going to act almost exactly like the exponential growth function. In fact, when we look at the equation, they look the same. Y equals a times b to the x, where a and b are just going to be some numbers, but that variable x is now in the power. And the thing about a is it still can't equal 0. It can be any other number, positive, negative, decimals, it doesn't matter. But b this time has to be positive and small. So in between 0 and 1. And it's when this thing is a fraction, when the base is a fraction or a decimal that's less than 1, that's what makes this function decay. So what does it mean to decay? Well, let's take a look at the parent function. Remember, with exponential growth, the parent function was y equals 2 to the x. Now it's going to be y equals 1/2 to the x. So that base is less than 1, but still positive. And we want to graph it, so how do we graph when we don't know how to graph? Well, we pick a bunch of points, like 0, 1, -1, 2, -2, and just plug them into the equation. So 1/2 to the 0 is just 1, because anything to the 0 power is 1. 1/2 to the first power is 1/2. And what a negative power does is take that fraction and flip it over. So 1/2 to the negative first power flips it over to being 2. 1/2 to the second power is 1/4, and so 1/2 to the negative second power is positive 4. When we start graphing all of these ordered pairs, the shape starts to show itself. 1 1/2, -1 2, 2 1/4, -2 4. And we end up with that same function as the exponential growth function. It's just with the exponential growth, it grew. It started small and got bigger. Now, with exponential decay, this function, the graph, is going to start big and get smaller. Once again, though, it still has a domain and a range that we want to look at. The domain, of course, is all the x values that we can use, and we can pick anything for x. So we say that's all real numbers. And the range is the same as with exponential growth as well. We see that this thing is going to get smaller and smaller and smaller, but it's never going to get negative. So there's this horizontal asymptote right here at y equals 0. So the range, since the graph stays above this line, the range is going to be that y is greater than 0. What happens when we start messing with the function? Like putting a -3 in front of it. Well, we can take those same values, 0, 1, -1, 2, -2, and plug them in. When we take 1/2 to the 0 power, we get 1. But now we're going to take all them results that we were getting in the y column and multiply them all by -3. So 1 gets multiplied by -3 to give us -3. We plug 1 in, we get 1/2 times -3 is -3/2. 2 times -3 is -6. 1/4 times -3 is -3/4. And 4 times -3 is -12. We'll start plotting all of these points. And we see we get that same decaying graph that kind of starts big and gets closer to the x-axis. The deal with this one, though, is that it kind of stretches out a lot quicker. Everything is 3 times as big, and this graph stays below the y-axis instead of above it. So when we look at domain and range, once again with the domain we can pick anything for the x values, so that's still all real numbers. But when we talk about the range, since that horizontal asymptote is still at y equals 0, and our graph stays below this line, we'd say y is less than 0. And how about the translations when we move everything around? Well, let's start with that parent graph one more time. Kind of the key point of this is the 0, 1, 1, 2, 2, 4, and the 1, 1/2, or -2, 4, -1, 2. But what's going to happen to this graph is all this shifting from these two numbers. First of all, this number tells us how far we shift our graph in the x direction. And so we're going to move this -2 in the x direction. This one, we take the same number that's there, -1, and that's how we're going to shift it in the y direction. So the opposite of what we see with what's next to x, and the same as what we see outside of x. So all we have to do with all of these points is shift them -2 in the x direction and down 1. So that's what happened to -2, 4. -1, 2 gets shifted back 2 and down 1. 0, 1 gets shifted back 2 and down 1. 1/2, or 1, 1/2 gets shifted back 2 and down 1. And what's going to happen to our graph is it's still going to decay, but it's going to look like this. Okay? The entire graph got shifted to the left 2 and down 1. So, how does that affect domain? Well, the domain is still going to be all real numbers because we could still pick anything for x. And graphically, our graph still moves to the left forever and to the right forever. But what happens to our range? Well, take a look at that horizontal asymptote. That horizontal asymptote shifted from being at the x-axis to being shifted to the left 2 and down 1. So now our asymptote is right down here at y equals -1. So our range, since the graph stays above that line, is going to be y is greater than, not 0, -1. Last thing, just some word problems. What about using the equations? All right, a snowmobile costs $4,200, brand new. That value decreased by 9% each year. Write the exponential decay model. Now we remember that the exponential growth model, we'll use a different letter. We use y. It was the starting amount and 1 plus the rate raised to a certain amount of time. And we used plus because that was growing. Now the number isn't growing. That rate is being taken away every time. So this will be what our kind of general exponential decay model looks like. And how does it apply to this problem? Well, the value is going to be the starting cost 1 minus the 9% that it loses every year for a certain amount of time. So if we want to find out how much the snowmobile is going to be worth in 7 years, we set up our equation. The value of the snowmobile is going to be 4,200. 1 minus 0.09 was 0.91 raised to the 7th power. We let the calculator do all the work. And we see that the value is going to be $2,170.39.